Hi, my name is Tan Jing Sen from RY41. I represent about PGT 212 Electronic Communication Technology for my mini project, Design and Analysis of Quadrature Detector Demodulator for FM receiver circuit. Okay, introduction to quadrature detector. This is the circuit diagram of quadrature detector. The quadrature detector is probably the single most widely used for FM demodulator. The quadrature detector is primarily used in TV demodulation. This detector is used in some FM radio stations. The quadrature detector uses a phase shift circuit to produce a phase shift of 90 degrees at the unmodulated carrier frequency. Okay, quadrature FM demodulator. This is the circuit diagram. They have capacitor, inductor, resistor, then another capacitor, mixer, and low pass filter. Okay. The circuit of quadrature demodulator is quite straightforward, consisting of mixer, a resistor, capacitor, and inductor. And there is also a low pass filter to follow the mixer, but this also can be quite straightforward. The incoming signal is split into two components. The first enter the mixer directly, but the second is phase shift. The phase shift is 90 degrees for the carrier, but the deviation on the carrier will cause the phase shift to change slightly. Dependent upon the amount of deviation, the original signal and the phase shift signal are then passed into a multiplier or mixer. Okay. Advantage and disadvantage of FM quadrature demodulator. The quadrature detector offers significant advantage for many circuits, but as with any decision, a number of different advantage and disadvantage have to be considered when selecting a given circuit for FM demodulation. Okay, advantage. Offer good level of performance and including line linearity. Okay, can be incorporated into an integrated circuit. Then for the disadvantage of FM quadrature demodulator, require to use a coil. This is not a major issue as a simple coil is used and an RF transformer is not needed as in the case of the ratio and Foster CD circuit. Some design will require setting during manufacture. So this is the disadvantage of FM demodulator. The design to setting during the manufacture. Okay. So this is my circuit multi-sim. Okay, have FM voltage, inductor, capacitor, then XOR gate, then oscilloscope. So the circuit demodulates a frequency modulator signal using an exclusive OR, means XOR gate, and a RLC phase shifting network, RLC circuit. The RLC network creates a phase shift that is a function of frequency. At FM carrier frequency, the phase shift is 90 degrees. As the frequency varies, the phase shift varies from 0 degrees to 180 degrees. This is my first circuit. Okay, for the methodology, I have two methodology. This is the partner methodology. So this is a step. Open multi-sim software, find FM voltage and set the radio to 5 volt, 1 kilohertz carrier frequency and 100 hertz intelligent frequency. Then the third one, DC voltage. We need a DC voltage, V2, 2.5 volt, connect to the output of RLC circuit and negative FM voltage. So next we require is a capacitor C1, 0.01 farad, microfarad, C2, 0.1 microfarad, inductor, 10 microhenry, then potential meter, 10 ohm, R2 resistor, 100 ohm, R3, 100 ohm. Then continue to C3 and C4 means capacitor 3 and capacitor 4 with 0.1 microfarad. Then connect a XOR gate parallel with the C1. Then output pin connect to low pass filter R2, R3, C3, and C4. Okay, so then put the voltage probe on the circuit PR1, PR2, PR3 until PR5. It means have 5 probe. Then use the 4-channel oscilloscope. where has 4 pins for ABCD. Connect pin A to the input from FM voltage. Pin B connect to output pin of the gate, XOR gate. Then pin 3 connect to the output of low pass filter. Then the last pin, pin D, connect to the output of RLC circuit. Then run and circuit analysis using interactive simulation. Interactive simulation is the normal one. Once we open the multisim, the standard is interactive simulation. Then double click the oscilloscope to get the pop-out of the output result and record the result. Then, well, for the probing result, we need to use the transient mode. So we need to change from interactive simulation to transient simulation. So for the probing result, if we need to get the waveform, then need to run simulation using transient mode with 0.00334 n time to get 4 cycles of the output waveform. So set the output of transient for the probe where PR1, PR2, until PR5 to get the different waveform and compare it with the theoretical simulation. Then record the output data. Okay, for methodology part 2, all the steps are same. Just the difference is the gate. If the first one we use is XOR gate, then the second one we change to amplifier. So in the multisim we call it OPM. Okay, then the rest are same. For the value of resistor, capacitor, all are same. Okay, so this is my output waveform. So for the circuit one, okay, this is my output waveform with carrier, then the four output. Then this is the transient loop. Same, have a carrier signal, then message, and continue to modulate and demodulate the signal. Okay, so this is comparison with the theoretical output. So my quadrature component is this graph, the middle one. So where I get is the middle, almost same. Okay, then for the transient, yeah, this is the transient mode. Okay, so this is my second circuit in multisim part 2, where I use the OPM. Okay, the mixer output is dependent upon the phase difference between the two signals. It acts as a phase detector and produce a voltage output that is proportional to the phase difference and hence to the level of deviation on the signal. So the circuit are the same, just the difference is the OPM and the gate, XOR gate are different. Okay, so the output waveform for the second part I get is the transient mode. So almost same with the comparison with the theoretical output. Just the difference is the graph has slightly curved. Okay, so I have researched that the curve is caused by the capacitor. The capacitor charging. So the graph that we get will be a curve a bit. Okay, so now I will present about lab simulation presentation using multisim. Okay, so this is my multisim. Okay, for part 1, circuit 1 is the XOR gate. So we'll be using is interactive simulation. So no need to setting anything. Just we need to prepare FM voltage, capacitor, then RLC circuit, then continue to the low pass filter. And this is the oscilloscope with ABCD pin, 4 pins. Okay, so the FM voltage I set is 5 volt, 1 kilohertz, and 100 hertz. So if we want to know the output, just double click, okay, then run. Okay, so this is my output for this circuit where I using the XOR gate. Okay, so 4 lines, 4 wave. One is carrier, and then continue to demodulation, modulation, and the message. Okay, so this is the output. If we want to use the transient, same, we can choose to transient, then change to 0.00334. Then for the output, 5 pin. correct. Please check this 5 pin. If we want only 2 also can for the comparison and the voltage, where is who leads either voltage this the amplitude or amplitude this voltage. Yeah. So we can get the answer by using transient simulation. So I press run, and this is the graph that I get for the transient simulation. Okay, so you can take it here and choose. Okay, so for the second part, I just change the XOR gate this to the OPM. Okay, so this is my circuit. Same, double click the output. For this oscilloscope, we will get the different different signal, so we can adjust it. Yeah, adjust it. Then okay. Okay. And continue to see. We can adjust it. Okay. So and the D, we can adjust to the middle. So this is my output for the OPM circuit. Okay. Then okay, then this is my interactive simulation that I get in the output waveform. Okay, so for circuit part 2, I will make compilation for the transient mode. So if transient mode, press here, interactive, change to transient, then the time limit. Okay, then the output for V1, V2, and PR1 until PR5, then press run. Okay, so this is the output result. Okay, for the transient mode. So this is due to capacitor charging. So the graph will be curved a bit here. Okay, so this is both graph for transient mode and interactive simulation. Okay. So okay, for my last is summary. So I or Q signaling refer to the use of two sinuate that have the same frequency and a relative phase shift of 90 degrees. Amplitude, phase, and frequency modulation can be performed by summing amplitude modulated I or Q signal. Quadrature modulation refer to modulation that involve I and Q signal. Quadrature phase shift keying can be accomplished by adding I and Q carriers that have been individually multiplied in accordance with the incoming digital data by +1 or -1. A final demodulate signal that is not affected by phase variation. Quadrature demodulation use two reference signals separated by 90 degrees of phase along with the two multipliers and two low-pass filter to generate I and Q demodulated waveform. Quadrature demodulation can be used to make an AM demodulator that is compatible with lack of phase synchronization between transmitter and receiver. So this is the amplitude modulation, right? means amplitude modulation demodulator. The I and Q waveform resulting from quadrature demodulation are equivalent to the real and imaginary part of a complex number. So the frequency of the modulated quadrature carriers does not change, but the baseband waveform that serve as the amplitude modulating signal do not necessarily have constant frequency. So the last one is quadrature demodulation can extract angle information that is relevant to both frequency modulation and phase modulation. So this is my presentation, okay, from introduction of quadrature detector to the circuit methodology, comparison, and the summary. Okay, so thank you very much. Thanks for the listening and stay safe.